morning, everyone. I would like to welcome you to the Art of YOLO workshop. I'll let our speakers introduce themselves. I really hope that this will be a great learning experience for everyone joining. Thank you.
Okay. Thank you, Umit. I guess I'll go first. Hi, everyone. My name is Katya Teodorovich. I am a machine learning intern here at Digirum. I'm currently an incoming second-year student at Purdue University studying computer science and math. And I don't know, not much else to say other than I've been working on running quantized YOLO models. So I don't know if Shashi would like to introduce himself.
Thank you, Katya. Hi, everyone. My name is Shashi Chilapagari. I'm the co-founder and chief architect at Digirum. We are a fabless semiconductor company developing hardware and software solutions for edge AI. So we wanted to organize this webinar to share some of the work that we have been doing on quantizing YOLO models and running them on edge devices. So Katya will be presenting a brief overview of what YOLO models are, what are the problems that people face when quantizing them. The approach that we found to be very useful in quantizing these models with very minimal loss, and also come up with a new slightly modified architecture of YOLO using different activation functions that is very useful for quantizing them. And finally, we are going to show some demos in which you can run these models on different edge devices. So towards the end, we are going to show how to run these models on CPU, on Google Edge TPU, and on our own Orca, all without actually having to buy or install any hardware or software. So to make the workshop, the webinar as interactive as possible, Umit already shared details on how you can also be part of the demo. So while Katya is running the demo, you can actually run all these side by side. If you can register for our cloud platform, you can get started with these demos. If there is any trouble signing up, when we go to the demo phase, Umit will be posting a temporary token that will allow you to run the notebooks. With that, I hand it back to Katya to provide a brief overview and then go to the demos.
Okay, thank you, Shashi. All right, so as Shashi mentioned, an overview of what we're going to go over today. We're going to start by sort of outlining the issue that we're working with, just going over the basics of what is quantization, what is object detection, what is YOLO, and then kind of combine all of that to see what issues we've been facing with quantizing YOLO models. After we see sort of the existing standpoint there, we will see our Digirum approach to reducing quantization loss for YOLO models, and how we were able to train quantization-friendly models, upload a lot of different variations of them, and make them available for use by all of you. So to begin with quantization basics, the point of quantizing a model is essentially to convert your tensors and computations from floating point data to integer data, so int8 or uint8. And the most evident positive or pro of that is to reduce storage size for your model. For example, if you have like a float32 model and you're reducing down to int8, you can tell that's 4 times smaller, right? So a big positive is storage size and memory size, especially if you're running on edge devices. Another positive is you get faster compute on certain hardware. In fact, sometimes hardware can only run integer models. So it's just a lot more friendly in that regard. And overall, just with smaller models, you get reduced latency and power. However, all of these positives do not come without their consequences. So obviously, quantizing a model will lead to loss in accuracy since you're squishing the same amount of data into a smaller number of bytes overall. And tool chains for quantization are not very stable. So it takes a while to sort of get it working and figured out. So there are different types of quantization, and this is essentially just almost different stages of reducing the size of your model. Float 16 quantization is basically what it sounds like. For example, if your original model is float 32, you keep everything in floating point, but you reduce it to 16 bits instead of 32. So obviously you get half the size with slightly reduced precision. Dynamic range quantization is just going to quantize the weights of your model. So none of the activations, but you're actually going to get integer weights for everything. So big reduction there, but not for the entirety of the thing. But what we're focusing on today is full integer quantization. So that includes the weights and activations for your model. Obviously, at the time of exporting your model, you don't know the precise details of what input you're putting in. So in order to do full integer quantization, you actually have to run your model on a representative data set to sort of get an understanding of like what range of numbers am I expecting to see when I input an image into my model. So you run your model on this representative data set and you generate this distribution of all the values that each tensor could have. And then once you have this distribution, you have to sort of reshape and modify it to fit within the parameters of whatever format you're quantizing into. So mathematically, once you have this distribution, you sort of dilate it and translate it to fit into int8 or uint8 or whatever that is. So that dilation and translation is represented by a scale and a 0 point for every tensor. So overall, pretty simple. Just subtract the 0 point, multiply by a scale, and now you have sort of a new domain for the values that your tensors are in. So this allows you to have a quantized model, smaller values, everything sort of shifted in this way, and obviously to use it later, you'll shift it back. So an introduction of object detection. I'm sure most people are familiar with this. Object detection, the problem here is to identify and localize objects in an image. The accuracy of object detection models is measured in terms of the ability of the model to classify the objects and the tightness of the bounding boxes compared to some ground truth. Later, when we introduce our models, you'll hear a statistic called MAP, that's mean average precision. And that's just kind of a metric to gauge the accuracy of this classification and bounding box detection. So object detection models come in two main variations. There are single stage detectors and multi-stage detectors. I'll start with multi-stage models. Essentially, this is two main stages. First, the model will find regions of interest in an image. And then once it finds those, it'll pipe those into a classifier to actually figure out what that type of object is. And you can see the examples listed there. And then single stage detection models will also, as they sound like, do all of that, but in one step. So it will predict the locations and the categories of each object and its bounding box. So YOLO, which stands for you only look once, as the name suggests, it belongs to the class of single stage object detectors. YOLO models have been used in a wide range of applications, and there have been many variants over the past few years, starting from YOLO v3 all the way up to v8, X, and S. And sort of all of this, all of this flexibility allows for the model to be used in a lot of different ways. The YOLO architecture allows a really flexible design and kind of lets it be used in a lot of different applications. Currently, YOLO models are maintained by Ultralytics. So they have YOLO v5, YOLO v8, and overall just their Ultralytics repo. And it's very well maintained, very well documented, and provides a code for easy training, validation, and export of YOLO models. Now, applying quantization to YOLO v8, Ultralytics has their export function, and they have an argument where you can export your models to int8. But when you run their official export script, here are the results you get. So the first results, we exported YOLO v8n float to ONNX to get an MAP of 36.5. And we also exported it to a full integer quantization TFLite format. And you can see here that MAP is 25.6. So that's a really significant loss from 36.5 to 25.6. Same exact model, the only difference is that you're quantizing. So the question is, why does quantized lead to so much performance degradation? To an extent, it's partially expected, but this is, more than is reasonable. If your entire MAP is 33, you don't really want to be losing 10% of that. And in order to get an insight into this, I'm going to share a window that has the architecture of YOLO v8. Okay. Can everyone see this?
Yeah, we can see that, yeah.
Okay, thank you. So YOLO v8, this is just the official exportation of a quantized YOLO v8 model. Has, if you scroll far enough down, 3 separate branches. And you can think of this as passing over the image with 3 different resolutions. So each resolution has a certain stride associated with it, and it will do certain convolutions to find images or find objects within that resolution. And each of these branches ends with a section here that has these 2 columns of convolutions, followed by concatenation, a transpose, and a reshape. These 2 stacks correlate to bounding box data and probability data, and then they are concatenated. And then you'll see the same exact section down here for the other resolution, and repeating again for the 3rd branch. And ultimately, all 3 of these are concatenated together into one big tensor, in this case with a size of 1 by 144 by 6804. Going back to our slides. So after we consider those 3 different branches, and each of those 3 branches having data for bounding boxes and probabilities, we have 6 separate tensors, right? So bounding box and probability data for 3 different resolutions. And we see that when we concatenate all of them and quantize that model, it sort of forces these 6 different distributions to be dealt with one set of quantization parameters. If you can see on the picture on the right here, perhaps it's a bit small, hopefully you can see it on your screen. But you can see that all the inputs and outputs of that concat operation are forced to have the same quantization parameters. That's the scale is 0.19 and the 0 point is 33. However, if you look on the left, those 6 separate tensors all have quite different quantization parameters. The scale goes all the way from 0.09 to 0.2. The 0 point goes from 75 here to 242 there. So you can tell that all this data has very different expected values, and yet you're forcing it to sort of conform to this one set of quantization parameters. So in our export, we kind of avoid this forcing by just cutting off the concatenation and outputting 6 tensors. So overall, a summary of our changes is basically to cut off everything beneath those concatenation layers. You may have noticed that there's a block of code at the bottom of the official export that translates it from 144 by 8,000 or whatever the number of predictions is to 84, in this case for 4 coordinates and 80 classes. So that's what we call the bounding box decoding logic. So we exclude that from the model, as well as all the concats above that. And we just deal directly with the 6 outputs that we get before those concats. So the code for our export is available at our fork of the Ultralytics repo at ultralytics.jurm. You should be able to click that link through the PowerPoint if you're interested. But overall, yes, it's just exporting the model with 6 separate outputs. So without forcing this one set of quantization parameters on one concatenated output, we can see the input or the effect that that has on MAP. So you notice that before we had about like a 10% drop in MAP. With our new model, we're getting an MAP of 33.6. So you can see like a slight drop from the original 36.5, but still nowhere near the 10% that we were losing before. Right. So now that we have this technique for exporting, we want to be able to export to all the different formats that we could possibly want, because we're greedy like that. So we have our Ultralytics.jurm fork, which allows you to use the same built-in Ultralytics export functions with our extra parameters to export to TFLite, a TensorFlow saved model, or ONNX. From ONNX or TFLite, obviously you could run that directly, or from both of those you could quantize and then compile for your specific hardware. And overall, just follow through these steps to get a bunch of different formats. Now, the models that we have trained and that we're making available also have one extra modification or option to make them more quantization friendly. And that difference is the activation function. So by default, YOLO v5 and YOLO v8 models use the SiLU activation function. And SiLU, I wish I had a graph here, but SiLU is an unbounded function. It sort of stays flat at the bottom and then just goes up and continues there. And since it's unbounded, and the whole point of quantization is to sort of force everything into a set of bounds, that sort of leads to a big performance loss. So alternatively, we use ReLU6, which basically just clipping your inputs from 0 to 6. And it's very quantization friendly because it's bounded. So at the JURM, we trained models with both SiLU and ReLU6 activation functions on multiple datasets, and we're making these all available to you. So an outline of the datasets that we trained on. There's 5 main ones. Obviously, the big one is COCO. That's just general object detection with 80 classes. And then we have 4 single class datasets. That's face, hand, car, and license plate detection. We found that these were pretty common applications that people used, and the data for them was pretty easily available. So all of those smaller datasets were trained on splits of open images, where we just downloaded the classes or the pictures with objects of those particular classes. As you can see, around 20,000 images for most of them, and trained our models on those. So we already have 2 activation functions, 5 data sets, and now we have 4 different model variants for each one of those sets. So from the Ultralytics repo, we have YOLO v5NU, SU, and v8N, v8S. So, judging the performance of these with all of the modifications that we made, including the ReLU6 activation function and the 6 output tensors, we can see very minimal loss from float to quant MAP. Obviously, you can read the table for yourself, but in some cases, like as little as 0.1%, going from 56.8 to 56.7 for our face models. So if you're in a situation where you need to quantize your model, this is a very friendly way to do that with very little loss. So I keep talking about these models that we've uploaded, And hopefully that leads you to want to actually use this. So the question is, where did we make these available? How can I use these models? How can I, integrate them into my own application? So this is where I will introduce the Digerum Delight Cloud platform. This is our platform that allows you to store and run model zoos on the cloud and run them through devices on our cloud device farm. This includes our Orca chip or Edge TPU, GPU, CPU, basically any device that we have available. And you can test these models on all of these different devices without actually having the devices yourself, just through signing up for our cloud platform. So I think the link has been dropped in the chat already, or you can click through the PowerPoint. You can sign up for our cloud platform, and then you'll have to generate a token for the demo that we have coming up. All right, and integrated with our cloud server, we also have the Digerum Pi SDK. This is, in essence, being able to access all of these instead of through a browser interface. You can access all of these through Python just by connecting to your model zoo, using your token, and then you're able to load any model and perform cloud inference and get all the results. So before I do the official demo, I'd like to share the cloud platform first. Okay, so this is the screen once you've already logged in. Hope readers can see that all right. When you log in, you won't have access to this many zoos initially, but you'll see the public ones. So the one that we are currently talking about is Ultralytic Speed 3. So you can see the different variations that we have available. You have different runtime agents, different device types, and float versus quant models. So let's say I want to run TFLite model on Edge TPU. I can select YOLO v5n Koku with ReLU6. Browse my files. I'll upload cats because that's the most generic example picture to use on the internet. I simply run inference, and in 26 milliseconds, I get my bounding boxes. The same process is repeatable for basically anything. You run a model on a Orca maybe. Two cats. And the same results are available on our chip. All right. So now we'd like to move to our Pi SDK demo, which we are making available through Colab. One second to get back to the slide here. So if you'd like to run the demo for yourself, you can click this link, or we can drop it in the chat. And this sort of just outlines the simplicity of using Pi SDK. It's 5 lines of code in the first cell, 1 line of code in the second cell to show all the different models that are available. And you should be able to try that out. So hopefully, if everyone has been able to click the link, then I can share my screen and run it myself.
Katya, maybe you can show once starting from cs.digerum.com how they can log in and generate a token also.
Okay. Yeah, so on cs.digerum.com, you can generate tokens. by going to Management and then My Tokens. You can see that we have existing ones, or you can generate a brand new one. I can call this demo, set an expiration date, or don't set an expiration date, but I'll make this one temporary for now. Then once we generate that token, we can copy paste into our Colab notebook. Then after installing our library, you will have the inference results for a specific image. So down here, you can see all the models that are available in the zoo. And any one of these models, you can just copy paste the name of.
Katya, can you make the screen bigger?
That was too small, sorry.
Yeah.
Okay. So right in here, I can paste this model instead. Paste quotation marks in there.
Maybe even a little bit bigger.
A little bit, okay.
Yeah.
And then rerun the same cell. And well, I guess that seemed to group them. But overall, trend is the same. You should be able to select any model. For the image, you can either, or in this case, you kind of have to do a URL since it's not local, but you could do a path to a local image or a URL to an image and a model, and all the code here stays the same, just same exact 5 lines. No, or here, let me just demonstrate that you can change the actual image that you're using. So again, you have model results for person detection. Here, this is still Coco, but that, I can try a hand model. And we see 6 hands on 3 people.
How about a face model too?
Um, three faces.
Yeah, I think for the sake of completeness, we can show the license plate and use the car.jpg image.
It's car.
Yeah.
The car. There you go. Car and change that to 8S license plate model. And we see the license plate has been inserted there. So just change the version, change the activation function, the data set, and all of those combinations are available through our zoo.
Katya, can you also show how the zoo.list models, you can filter them out by the device type? So zoo.list models device equal to, let's say, CPU, yeah, Edge TPU.
You can see the list of Edge TPU models. CPU. More CPU models. Okay. So go back to the PowerPoint. For one final slide to just sort of summarize all the resources that we have available and just where you can access all of this for yourself. So our cloud platform is on cs.digirum.com. Should be a pretty easy sign up process, and our zoo is public, so you can access all the models from there. The notebook that you had on Colab, as well as a few other example notebooks using our PySDK, are available on github.com/digirum/PySDK examples. In order to run this with your own devices, make your own AI server, you can look at the Docker link there. And I'd like to note one extra thing. Right at the bottom here, we have a Python wrapper. This is if you, for any reason, don't want to use our PySDK. All of the post-processing that we sort of ripped off of the model itself, we re-implemented it in NumPy. So this is a pretty lightweight repo, about 250 lines total, I think. And it just kind of demonstrates that we're not really doing anything special, just a few lines of NumPy code to get it back to the same format as the original export output. And this YOLO inference repo, I can actually show right here. YOLO inference repo also has a sample of these models in the releases. So I think this is just the Coco and face detection models. So that way you don't even have to go through the platform. If you just want to try one of them out, you can example here and run it through the instructions listed in the README here.
Yeah, maybe you can show the example notebook just to see it's again only three lines of code, I guess.
Yeah. So yeah, I tried to mimic the sort of interface that we have with PySDK here. So you just load the model, get the results, and get the image overlay. And I think that just about includes everything I wanted to go over. Shashi, do you have anything to add?
Thank you, Katya. I think since we have a few more minutes left, we can open it up to Q&A to see if people have any questions, whether they want any more resources. If somebody has a request to see something extra in the demo, we can accommodate.
Thank you, Katya. Thank you, Shashi. Yes, if you have any questions, please put them into chat and our speakers will respond. Thank you for joining us this morning. Actually, I have a question. Are they able to see the inference time for different devices for the models so they can see if it makes a difference in which platform you run these models? Are you able to show them, Katya?
Yes, I can show that now, actually.
Okay, I think that's one good data point.
Okay. All right. So going back to our cloud server, when you run a model through the cloud server interface, you can just select any image you like, run inference, and down here you will see the inference duration. So on Orca, it is 11 milliseconds. That was V5NU ReLU6 Coco. I can check the same model on Edge TPU. Same image. You can tell that sometimes the first inference has a different duration than the next one. So this one took 18 milliseconds. And for some contrast, I can run a CPU model as well. That is 52 milliseconds. Going all the way up to 80. And not giving results.
Because this is a car model. So
oh, that's a car model. Thank you. Coco.
Yeah, so that's the other thing that we observe is that the CPU times can vary, whereas edge accelerators, so since they are just dedicated for running the ML models, so their times are much more repeatable.
So
can they see the code to run this locally?
Yes.
Yeah, actually in the browser itself, you can expand the yeah.
So we go here, basically these 3 lines that you're probably familiar with from the demo. You can configure any extra options and then run the model and show the overlay.
And
then when
sorry, go ahead.
I just wanted to add, if you're running this code locally, you can also say model dot, I think it's measure time. We have an argument, and then you can actually see the timing results through PySDK as well.
Yeah, Katya, maybe you can just show our document page also so that they know all of this is documented.
Yeah, sure.
Umit, there was a question that whether this thing is being recorded and whether the recording will be available.
Yes, we are recording the meeting. There will be a replay of this session with live Q&A, and we will announce it, and we can also send you the recording.
So yeah, we have our documentation page here. And if you go to PySDK, user guides, you can get the API reference for the newest version of PySDK. And this has all the details for how to run local inference, cloud inference, just everything you could possibly want to configure when running these models.
There's a question, Yusuf asks, can license plate detection also detect the license plate numbers?
The model that we have currently just...
Yeah, so maybe Katya, you can go to the model zoo and go to the YOLO, our public model zoo.
Sure. This one? Or?
Yeah, so there should be a detection YOLO plates. You can filter it on the top. Yeah, so we have an LP OCR.
I don't know if I.
We have on our images, we have a license plate image that we can. Yeah, this one wouldn't work because, yeah, it is too. Maybe I can share my screen.
Yeah.
Just a second. I'll start sharing my screen. So typically the license plate detection is done in 2 stages. So in the first stage, the license plate detector is used to detect the license plate. And in the second stage, we have an OCR model that is also YOLO based that can be used to read the license plate. So again, this is this 4XX8538. This is the license plate that you saw on the car that Katya showed before. So you run the license plate detector on that car, you crop the image, and then send it to the OCR model. And you can see that it can read the license plate. So it's a two-stage approach. First stage detects the license plate, second stage reads the license plate. So we have 2 YOLO models, and this model is actually today available in our public zoo. So when you go to the models, whatever are the public models, everybody should be able to access them. So you have the public models where we have a lot more variety than the Alterytics thing that we shared. So we have classification models that have all the standard efficient nets, mobile nets, res nets, ResNet 18, ResNet 50. We have detection models that vary from efficient det, mobile net. And then we have YOLO based models that have a bunch of YOLO models that we have trained for different purposes. Cocoa, car detection, animal detection, birds, desert, fruits, household objects, license plates, pets, and so on. And then we have pose detection models. So based on MobileNet V1 pose, and we have a couple of, we have like a segmentation model based on Deep Lab. Again, mainly working on Orca and on CPU.
One of the guests asking if they can use video to run those detection models.
Yes, absolutely. So
can we show them if possible?
Yeah, so this demo was not set up for that, but in the browser, we cannot use the video. Browser doesn't have access to the video, but we have other PySDK demos. Our PySDK examples repo actually has things that are working with videos. So you can run a video file. You can do an RTSP camera stream. You can run from a webcam, or you can run like a YouTube URL.
I just shared the link to our YouTube channel. It has a few of those example demos while you can use a detection model to run on the video feed. Let us know if you have any other questions for our speakers today.
Okay, since somebody asked for a video demo, I think it's our responsibility to show it to them.
I think so. Yeah, if you're in a position to do it, yeah, let's do it. We have time for it. Thank you.
Yeah. So you can see my screen, right? So this is a notebook that is running two different models, a face detection model and a hand detection model at the same time. So again, the code to run this model is extremely simple. So again, this example is available on our PySDK. So you have the PySDK Digirum package. You connect to the model zoo. So that means actually this demo that I'm showing now is running through the cloud. And through the cloud, it is providing you about 30 frames per second on two different models. So that means you can actually really develop real-time applications in the cloud. And then after you decide that everything looks good, you can actually buy the hardware and deploy exactly the same code, only one line change. So if you go from cloud to local, you just need to change this one line of how you connect to the zoo. So you connect to the model zoo, you specify the models. So you have a hand detection model and a face detection model. And we basically have very simple API that says
Could you
for
zoom in
hand.
a little more? The code is not readable. Much better. Thank you.
Yeah, so as you can see, the code is very intuitive. So we have a predict batch function that takes a video stream as an input. So to the hand detection model and to the face detection model, you pass the video streams and basically say for all the hands and faces detected by these models, overlay them on the image and show them. So, and in these four simple lines of code, you can see two separate models running, their results added and then shown together on the screen.
Thank you, Shashi, for showing us another impromptu video demo. That was really helpful. I think with this, I would like to thank our speakers as well as our guests to provide us with such insightful and practical information on how to quantize these models. I know that the community has been having problems quantizing V8 models with these performance losses. So this is a great contribution to YOLO community. And at any time, our guests can contact us through hello@digiroom.com. We'll be happy to respond to your questions. Thank you so much for joining, and we'll hope to see you in another educative webinar soon.
Thank you, Amit. Thank you for organizing this.
My pleasure. Have a great day, everyone. Thank you, Katya.